So today I'll be talking about NUPEA. This work was done during my internship at Efficient, and we are a startup spun out of Carnegie Mellon. We're commercializing an extremely energy efficient hardware software stack. And so if you want to find out more, take a look at our website, efficient.computer. All right, so let's start with an overview. So data movement is the dominant bottleneck in building scalable parallel systems today. Modern conventional systems manage data movement by moving data close to compute, usually by distributing the memory hierarchy, like with caches or with non-uniform memory access or NUMA architectures. This way, some data is close to compute, but most of the data is still far away. And so to take advantage of these architectures, we need to smartly place data, which is a very tricky problem. And so what if we thought about scaling data movement differently? What if we move compute or even individual instructions close to data? And so there's been some prior work in this arena, like with near data computing, where threads migrate to data, but it needs brand new hardware and software, and it hasn't caught on in newer systems today. And so in this talk, we'll look at data movement in the context of spatial dataflow architectures, or SDAs, an emerging general purpose accelerator platform. And for SDAs, moving instructions close to data is actually a very natural thing to do, and doesn't beg for completely disruptive changes to the full system. And so let's see why. And so a conventional von Neumann core will run a thread, which runs a stream of instructions, but spatial dataflow architectures are different. And so instead of a core that executes an instruction stream, SDAs distribute its compute spatially into processing elements, or PEs. Instructions are distributed onto those PEs, and they communicate directly with each other. And PEs run just a handful or even sometimes a single instruction for the duration of a program or thread. Now let's think about how SDAs access memory. So small architectures like this one implement what we call uniform PE to memory access, where it takes a set time for a PE to access memory. If you have a load like the one at the bottom, abbreviated LD, that tries to access memory, it'll be fast since everything is kind of nearby each other. Now, what if we scaled our compute up to a lot of PEs? So this time, let's have these two loads access memory. But unfortunately, both of these accesses are going to be slow. And so why is that? So if we naively scale to a large architecture, the uniform access latency will need to slow down to handle the worst case, which is this load that crosses the entire grid of PEs to get to memory. And so which means we're going to slow down all memory instruction. And so SDAs do have this data movement scalability problem. And to address it, we need to answer the following question. How do we scale an individual instruction's communication with memory? And so in response to this problem, we had two insights that led to our solution. The first insight is some PEs are just closer to memory than others. And the second one is that some memory instructions are just more critical to performance than others. And so these insights led to our solution, which is NUPEA, non-uniform processing element access. And so NUPEA architecture segments compute into domains of non-uniform access. And so here the domain of PEs closest to memory will have super fast access time, but the domain a bit further out will be a bit slower by design. And NUPEA allows us to scale compute. So like if we wanted to add this extra domain of PEs, we can do so without slowing down accesses for all PEs to the worst case. So to take advantage of NUPEA, we want to move only those few memory instructions critical to performance to this small slice of PEs close to memory. And so NUPEA enables this instruction-centric approach to scaling data movement, where we move instructions to close to data, not the other way around. And because we're moving instructions, NUPEA relies on the compiler to find critical instructions and prioritize them for fast domains. And this is actually a tractable thing for the compiler to do, because it's much better at reasoning about program analysis than about data that it doesn't have access to at compile time. And so to put all of this together, we've implemented Monaco, a NUPEA spatial dataflow architecture that you see on the right. So Monaco has NUPEA domains listed at the top, with D0 being our fastest domain, able to achieve zero-cycle PE to memory latency. The Efficient C compiler, or FCC, is a parallelizing compiler that takes advantage of these NUPEA domains and finds critical instructions across threads and places them in fast access domains during place and route. And so both Monaco and FCC are industry products from Efficient, and Monaco was recently taped out and deprecated. And so to highlight a few headline results, against a realistic uniform PE access or UPA architecture, Monaco achieves a 28% speedup across a variety of workloads. It also achieves a 20% speedup against a similar UPA SDA with NUMA domains. And adding NUPEA awareness to FCC gives our workloads an average 25% performance. And so here's what I'll cover in the rest of the talk. So I'll highlight some basics about SDAs. We'll look at the SDA data movement problem. We'll look at NUPEA, Monaco, FCC, and then we'll evaluate. All right, so let's walk through some basics, especially about SDA compilation. So we'll have a running example for the rest of this talk. which is this linear search program. And so the for loop here looks for key in a list, and it stores I to index if it's found. And so for an SDA, we compile to a data flow graph, or DFG, of dependent instructions. And so for instance, the highlighted code here compiles to this subgraph. And so we have an iterator instruction that manages I. And the way this works is that I fires its initial value of 0. We check if it's less than n. And the value of I gets steered into the body of the loop. And so SDAs commonly use these steer instructions, which is that triangle at the bottom, instead of branches, so that all data values are explicitly routed to their instructions, or their destinations. The rest of the DFG is kind of straightforward. We load from the list and compare to key. If it's true, we store I to index. Otherwise, we steer back the update to the iterator. And so the last step of compilation here is place and route, or PNR. And in PNR, we map the DFG onto a fabric of PEs. And so this is the example PNR result for linear search. And so during this phase, PNR tries to minimize the routing delay, number of hops, or some other objective function. And that's an important takeaway here. PNR is already incentivized to place dependent instructions near each other and localize communication. And so this is an important piece that you want to keep in mind as we think about localizing communication in memory later. All right, so now that we have some basics down, let's see the data movement problem in SDAs. So recall from the overview that small SDAs can afford this fast, uniform PE to memory access. And so I want to show you what happens if we scale the fabric, but still maintain that uniform access latency. So we're going to use this example program. And what we'll do is we'll parallelize it using a parkour. We're going to map this program onto this larger fabric. But to keep things simple, I'll try to zoom into just a slice of the fabric, this 6x6 at the top right. And so what I've done here is I've taken the PNR result for linear search and placed it in the top left quadrant. This really just corresponds to one of the threads from the parkour, though. And we can fill the rest of the 6x6 with 3 more threads. And so we're interested in memory accesses, though. So I've grayed out all the other instructions except for the load and store from each thread, which amounts to the 8 instructions that you see highlighted on the fabric. Now, all of these instructions can access memory, but they'll be slow because of this large fabric, and uniform access latency on this large fabric is slow because we have to handle the worst case. So the latency is slowed down to the one all the way to the left, or if it's an even larger fabric, much further than that. And so this begs the question, why is it so challenging to scale with uniform PE access, or UPO? Well, trying to maintain low latency will run into problems of high wire delay, forcing the system to run at a low frequency. It might also be difficult to close timing in digital and physical design. And so we can address those problems by adding more arbitration to memory, but that would just increase the UPO latency overall. And so it's just a lose-lose scenario. The impact on performance is also particularly bad for this program. And so let's take a look at the DFG to see what I mean. So the load in this program isn't just some instructions. Its latency controls the performance of the entire thread, because it's on this recurrence that controls the loop iterator that I've highlighted in red. And so if that load is slow, we can't start another iteration for 6 cycles, granted that each step along this recurrence takes a cycle. And so note that if the store is slow, we don't have the same impact since it's not on the critical path. And so if we up our UPO latency, the performance degrades very quickly. And so we call this kind of load a critical load because its performance controls the performance of the whole program. And so all in all, scaling an individual instructions communication with memory is difficult if you want to maintain uniform PE access. And it's especially bad with critical loads. All right, so let's see NUPEA in action then. So recall that we built this intuition for NUPEA using these 2 insights. Some PEs are just closer to memory, and some instructions are just more critical. And so let's exploit insight number 1 to solve the problem for this program. And so if some PEs are closer to memory, what we can do is we can segment them off and give some of the PEs fast access. And so we'll add non-uniformity explicitly in the architecture. And so in our example, SDA, we got 2 domains here. D0 can get to memory in no time, and D1 takes 2 cycles round trip. And so this is nice because some of our accesses are going to be faster, but not all of them. So accesses in D1 are still going to be slower, especially for those critical loads on the left. And so that leads us to exploit insight number 2. We can move individual instructions close to data. And so NUPEA Aware Compiler can find critical loads using common techniques like recurrence analysis. And we can take those critical loads across threads, and we can put them in fast access domains. And so what we've done here is we've shifted all the stores to D1 and the loads to D0. And that's okay, because we can now achieve the minimum time of 6 cycles to get to the next iteration. We don't need to worry about the stores because they're not on the critical path. And so this is the benefit that you get from NUPEA. And so let's take a step back and look at how NUPEA shapes up with other approaches to scaling data. And so data-centric approaches where data is moved close to compute need smart data placement, which is really difficult. And so modern systems have static NUMA or static NUPEA techniques, which interleaves and distributes memory, but that's usually not good enough. There's been decades of work to improve on this, but you often need the whole stack involving the OS, compiler, and the programming language to accomplish what you need to do. In contrast, NUPEA just needs the compiler. And so we can analyze program instructions and get a long way by taking those critical loads and then placing them in fast access domains. Now, this is not to say that NUPEA is just a standalone technique. NUPEA can be complementary. If you want to scale the memory hierarchy with your SDA, you can do so. All you need to do is change your NUPEA topology. All right, let's take a look at Monaco and FCC. So I'll give the highlights for Monaco, our NUPEA SDA, but you can find out more in the paper and on our website. Monaco is a 12 by 12 fabric with heterogeneous PEs, a uniform memory, and a combinational data type. Each PE has multiple functional units, or FUs, which run an instruction or two for the duration of the program. Each PE has a basic FU in white, and an arithmetic FU, which is in blue, or load store FU, or LSFU, which is in this light teal color. And so Monaco has rows of alternating LS and arithmetic PEs. Monaco also has 4 NUPEA domains. And so domain D0 can achieve 0-cycle fast access and single-cycle loads. And Monaco implements this disaggregated fabric-to-memory arbitration network to carry requests to and from memory and also manage your NUPEA domains. And so we can zoom into one of these rows of LS showing the request side of the network. And so a couple of things to highlight. We've flopped arbiters at the head of each of D1 to D3, so we can break up the critical path to memory. And D0 isn't flopped, so we can achieve 0-cycle PE to memory access. And so Monaco's NUPEA topology allows LS to be spread across the fabric without slowing down all memory instructions. And this ends up being good for PNR. This way, some LS will always be close to other PEs, like arithmetic PEs, so then PNR can continue to localize communication. FCC generates optimized DFGs from C code using MLIR, and it automatically parallelizes loops. FCC is also NUPEA aware in our system. So it takes Monaco's fabric topology as input when it does mapping in PNR. And FCC identifies critical memory instructions that place in fast domains during PNR. And so we found that using pretty simple heuristics got us a long way. So we look at 2 categories of instructions: loads along loop recurrences, which are the most critical, and frequently executing inner loop instructions, which are also prioritized. All right, so with that, let's evaluate. So we simulated a variety of workloads on Monaco and 3 NUPEA SDA baselines with the same fabric size and PE mix, which I'll describe more in a bit. And so we used the in-house microarchitectural simulator that we built for design space exploration of Monaco and other alternative designs. And we measured performance of the baselines in PNR. And so our main takeaway is that Monaco is fast. And so on the left, we plot execution time normalized to Monaco. The bars here are geomeans of our workloads, and here a shorter bar is better. And the baselines here are all NUPEA SDAs. And so to give some more detail about these baselines, the first one is an idealized one, where we can achieve single-cycle loads no matter where you are on the fabric. The next baseline is a realistic NUPEA SDA, which needs at least 2 levels of arbitration on the request and the response side, which amounts to at least a 5-cycle round trip per load. And the final baseline is that realistic NUPEA SDA, but with 4 NUMA domains. And so on average, Monaco was 28% faster than NUPEA, 20% faster than NUMA, and within 21% of ideals. And so here's the execution time numbers for all our workloads. I just wanted to highlight just a few of them. So our sparse tensor programs, that's highlighted in the middle, had many critical loads, and Monaco performs well. But also importantly, it's really close to ideal because we've accelerated those critical loads through fast NUPEA domains. Monaco also does well on other kinds of workloads, like dense workloads, like these DNNs from the ML Tiny benchmark suite. And we offload inner loop loads to faster NUPEA domains to also get good speed up. Our other main result is that FCC's NUPEA-aware PNR improves performance. And so we evaluated 3 heuristics to vary whether the compiler is aware of NUPEA and aware of criticality or critical loads. And so on the left, we plotted speedup over the NUPEA unaware, criticality unaware, or NUCU heuristic. And so here, taller bars are better. And these are the geomeans for all our workloads. And overall, FCC improves performance by 25% over the completely unaware heuristic. Once again, these are the speedups for all our workloads. I just want to highlight the same workloads again. So for these sparse ones, it's clear that NUPEA awareness is not enough. The best bar is the one with FCC. And so this means that knowing which loads are critical and placing them in fast access domains is what unlocks the most performance. On the other hand, with these dense DNNs, NUPEA awareness is enough to get high performance because there's very few critical loads to begin with. And so FCC just saturates fast NUPEA domains with as many loads as possible. There's also a lot more that you should read about in the paper, including more on our NUPEA topology, sensitivity studies, and more. All right, so today we talked about NUPEA, an instruction-centric approach to scaling data movement, where we move instructions close to data. Monaco and FCC are industry products from Efficient that use NUPEA in practice. All right, thank you. I am open to questions, and I just want to say we are hiring, so please check out the QR codes for more details.